Good. I'm just going to mention, I worked in spinal cord injury for 25 years, brain machine interfaces. I'm doing some work in Parkinson's now, so I'm kind of neuro adjacent. But I'm coming to you tonight actually as a robot engineer. The second thing I want to mention about tonight's talk, this is not a polished talk. This is most of the slides I just made up in the last few weeks. This is new material. I'm right in the middle of it. And it has to do with prediction. It's one of the things that I do that might have some kind of overlap with your community. So for those of you who aren't familiar with American culture, there's a well-known person from my generation named Yogi Berra. He was the king of malapropisms, which means mashing together words that don't belong together to a humorous effect. And so he made famous, it's tough to make predictions, especially about the future. And that's the title of my talk. Although people found out later that Niels Bohr said that earlier in the 20th century. And not only is he a famous physicist, but he's Danish. And apparently, it may be as early as the 11th century that this phrase came up. If anyone here knows Danish culture, please let me know. All right. These days, because robots are hopefully, I don't know hopefully, but are going sort of everywhere and working in human environments, there's a whole community that I belong to called safety critical control. And so the idea is as these autonomous systems go out in the world, they have to sort of make predictions about all kinds of other moving agents. So certainly in autonomous cars, driving on the highway, how to merge, et cetera, change lanes. If you're in a kind of an urban environment, worrying about where pedestrians or bicyclists may go. And so it's one thing to make predictions. Anyone can make predictions. What's hard about predictions is to make them in a safety critical way so that actually you can get guarantees that you won't hit them. Again, as much as any engineering theory has a certain guarantee to it. In addition to sort of autonomous cars, some of you may have seen these autonomous food delivery sort of vehicles around here. This happened just recently in Los Angeles, in my city. I don't know if this made your sort of news. So this was, I don't remember the company. They were actually delivering food going across. They had a pretty good prediction algorithm. And then a Waymo car comes around the corner and whacks the thing. And what was cool about it is you'll see the little delivery vehicle actually figured out how to get away and continue on its path. And the Waymo is not smart enough to call for help. So this is, I'm going to show you guys later a longer video from a series of competitions I was in. We were exploring underground spaces. This is in a coal mine outside of Pittsburgh, where we had a team of all different kinds of robots exploring this 8-kilometer mine. You'd be surprised. We thought over 8 kilometers of robots would never see each other. Of course, they came together and smashed into each other.
This is the subterranean challenge.
This is one of the subterranean challenge events. And because the guys couldn't communicate with each other, or they weren't able to know what, predict what other robots might do, right after the end of this vehicle completely obliterated our drone. So now I know what the inside of a LiDAR looks like. Another one, at least in the US, and I don't know about Europe or Asia, there's lots of talk and maybe now even some movement to start to make sort of much more automated air traffic control systems. And so while the motions of these vehicles are highly controlled, there's still always lots of times goofy people who fly their drones into an airspace or people get in trouble. And so there are sort of unknown things that, again, be good to predict. I recently joined a drone racing league and collaborate with a team in Abu Dhabi. So this was back in April, the first race of this league. This is a multi-drone league where you have to fly through gates, as you'll see in a second, and make sure you don't hit the other ones. I'm happy to say you'll see our drone is the one out front. And mainly our strategy here is just go like hell and hope no one catches you.
And it's really dark like that?
It's pretty dark, yeah. What's fun about this league is next year we'll be actually going outdoors in the wind and stuff, and they'll be having moving obstacles on there, and actually both human and autonomous pilots at the same time. So unfortunately, you can't hear the sound. It's loud as hell. And so these drones get to about 20 meters per second. So this is all autonomous. There's no humans involved. They know roughly where the gates are, but they actually scooch the gates a little bit before the flight. And so the idea, of course, is whoever survives and then sort of lands back in the starting zone first, wins that particular race. And so our obstacle avoidance strategy here, or prediction strategy, was sort of quite naive. But in addition to avoiding obstacles, lots of people are proposing now that robots can sort of team with sort of humans. Many of you may have seen this in the news. This is just a few months back. Several humanoid robots actually helped run a marathon, a half marathon in China Apparently, I just found out yesterday after this event, robot sales in China doubled in the weeks after this. And so you can imagine, again, these humanoids, at least to have some knowledge about what's happening around them in the future. Right now, they had someone with a joystick, sort of
Somebody's driving them.
steering them. Yeah, they ran on their own. Okay. All right, so humans, animals, and even neuroscientists, like in Claire's talk yesterday, are constantly making predictions. And so prediction is a huge field. I'm going to give you a very narrow mechanical talk tonight. It's about sort of predicting dynamical systems. But I'm hoping some of the techniques are a little bit new, and they may sort of find uses in sort of other locations. So I'm going to use two model organisms as sort of running examples here. So the first one is I work on autonomous drones, as you saw, and we were actually flying outside in a field at Caltech, but not autonomously, just to gather some data. And some jerk little kids, these are like eight-year-old boys, actually, while we were flying around, threw footballs and threw frisbees at us and all this kind of stuff. And so, we obviously piloted around it and yelled at them. But we thought, hey, wouldn't this be a good thing if in the future they could sort of autonomously sort of avoid these things? Now, or if you throw something ballistically like a football, it's been known for decades actually how to avoid a ballistic object. But things like frisbee, depending on the spin rate, they have very complicated dynamics. And so it's very difficult to predict. So we asked the question, could we, not only for these ballistic type things, but just general other people or drones, learn a model on the fly? Now, so this is kind of a fun project. This is next project. Let me first mention is that and I'm going to give a problem definition. What we want to assume is that we actually don't know too much, and that everything we can measure about these obstacles as they come towards us is actually very noisy. So we want to develop a theory. Can we learn on the fly, handle sort of noise and uncertainty, and get guarantees, because that's our job of sort of safety of our ego vehicle, as we call it. So this is what pays my bills. Unfortunately, like it or not, in the US, most robotics research is funded by the military. I apologize, it's just sort of the way it is. And so right now I'm involved in a project called Link. And one of the tasks that we're looking at is actually out in the deep oceans, resupplying sort of large boats. So these 900-foot boats take a lot of food and fuel. And then if the seas are calm, this is actually how they resupply them. I'll come back to this in a second. Some of my team actually went out on a Navy supply mission last fall. What most people don't know, there's actually a whole 5,000 person unit of the US Navy that all they do is supply boats. And it's nuts. What they do when the weather is calm is they actually shoot a zip line across, and they just ferry food and actually 50,000 gallons an hour of fuel between the two boats. But when seas aren't calm, the ships have to turn around and go back into port and refuel and go out. In addition, one of the difficulties they have is when they go out on a mission, they have to load lots of things into the boat. One of the things they have to load is a Tomahawk missile. Again, I know you guys think I'm this horrible warmongering sort of person here. What's difficult about this is they have to load them into these fairly narrow, tight silos. It takes them an hour per missile, and they typically have to load 24 missiles, so it takes them a full day. And so what they'd like to be able to do is not only can we transfer stuff between boats, when they get called into a mission and all of a sudden have to load up, whether it's missiles or other things, can they just dump stuff on the deck? And while you're underway, can you actually, in sloshing seas, load all this stuff using onboard cranes? And so the way that we simulate that right now is in my lab at Caltech. We have this sort of dynamically scaled crane. You'll see it a little bit later in a different video. This actually is a 6 degree of freedom motion simulator, like you would see in a flight simulator, that sort of simulates the wave motion. This crane is scaled to be the sort of same size as on a boat if this were a Tomahawk missile. So this is our scaled Tomahawk missile. This is our little silo down here, and we have sort of lots of obstacles in the way. And so what's happening then out in the open ocean is we don't know what the sea state is. And so without the control system turned on, this Tomahawk missile is sort of very wild. As soon as we turn the control system on, then an operator, so the Navy always has to have a human in the loop. We could actually do this better autonomously. But now the operator is trying to guide this faux Tomahawk missile into the silo. And then this is sort of simulating the sea state. I don't know why this video is so slow.
It's because it's Zoom.
Yeah.
If you turn around your laptop, people will see the real time. In the audience, at least.
Okay.
Kind of see it, at least.
What we sort of figured out the hard way is, this looks like it's just naturally following this. If we didn't have a control system and a predictor in here, this thing would be going all over the place. So if we can actually in real time predict actually where this thing is, we can actually then make it very easy for the humans to sort of do this. And you can do this autonomously, this is how we would do it. So how do we sense the state of this? We actually have two sets of cameras. There's the cameras watching the profile. We have a real-time vision system that's measuring the location of this 20 times per second. And we actually have another vision system here, which is actually been tracking sort of the target down here and using that information. And then on the platform itself, what we would actually have in a real application is only a simple IMU, basic accelerometer gyro. So we actually don't have any measurements of where this platform is. All we have is this gyro on here. And anyone who's played with the gyro knows they're really noisy. So now the question is how can we actually predict where this C state is, how this thing is going from this really sort of crappy sensor? And so that's what I want to kind of talk about tonight. Okay, so I'm not the first person on Earth to do mechanical prediction. So the common ways that people do it is that actually, if you know the thing that you're trying to either avoid or track or hit has a ballistic motion, then you can use the known ballistic equations, and all you have to learn on the fly is just a few parameters just to decide sort of what is the air drag and what's the arc, et cetera. It works very well. You'd be surprised, a lot of expensive Navy radar tracking systems use what we call a stochastic acceleration model. They basically say, we don't know what the dynamics are. So we'll basically say, where the position, velocity, acceleration are at the next instant is just where they were the last time, plus the delta t or delta t squared over 2 times 2. And then assume this is driven by noise, but then you use a common filter to kind of make up for your sins in tracking this. It's very common these days in the kind of, and many of you know more about this than I do, is to actually use large network models to actually basically learn a large language model of time series. So basically you take a big net and you train it on every time series you get your hand hold of. And actually then as a new time series comes in, it tries to predict what's the closest time series to the data that it's seeing. For mechanical prediction, it does work very well.
Does not work well.
No. And so what our goal was to learn a model on the fly. There's some good things about these. We're actually looking right now to actually combine what I'm going to talk about today with these. So these are good if you know nothing ahead of time. But what we're trying to do is to figure out, can we actually make a system that can actually learn the dynamics kind of in real time. And when I mean real time, I mean real time, because if this thing's coming at you, you got to sort of figure out, how do I learn enough about it to get out of its way? Okay, so here's some of the issues that we have to kind of deal with as safety critical control engineers. So we want to be able to kind of predict the obstacle dynamics, and dynamics is one thing, so that constrains what the vehicle can do. But in addition to things like footballs and badminton things, if there's actually another drone, there may be a controller on there, and so there's some intent. So we actually have to also kind of learn what the intent of this drone is. We're only partway through that now, so this is an open issue that we're still struggling with. And we want to assume that we actually can't measure all the states of what's coming at us. Well, what we can do is we can actually measure using computer vision cameras. That's easy to do. Sort of a time series of just some point on the obstacle. It's X, Y, Z location over time, and then we assume it's sort of corrupted by noise. And so we don't actually know the dynamic class ahead of time, so we want to sort of learn what is the sort of dimension of the dynamical system and something about it. And then we have a limited amount of observation time to actually learn this model before we get hit. So it's got to be fast. And again, I'm not going to go too much into safety theory tonight, but we want to then sort of learn this in a way that we can guarantee that we can avoid it being hit or successfully rendezvous it if we want to. Okay, so here's the problem statement, and then you can doom scroll your phone or do whatever you want to do. The rest is sort of details, but you'll wake up at the end. I have some fun videos for you. So here's the idea. So our drone or ground vehicle or any robot is given some tasks. So it's got like a figure 8. You'll see this in some of our experiments a little bit later. And so that's given to us. And then any real world vehicle as a control engineer doesn't have unlimited control authority. It doesn't have unlimited speed. So we actually have some constraints on it. We have some stage costs. So in RL, this would be, we have a reward function. So we have some way we prefer the vehicle to kind of behave. And then we assume that there's a bunch of obstacles coming at us. For today's talk, we're going to assume that actually, no matter what their shape is, we can bound them with some sphere, but actually a very tight sphere. We actually will estimate the size of the radius of the obstacle. And so what we'd like to do, and this is the second part of my talk, is talking about risk. Given a risk tolerance, so zero, sort of one means like absolutely I can take no risk. Actually, I'm sorry, I can take a lot of risk. Zero means I'm very risk averse. Given a risk tolerance, can we actually construct a control system that I actually can, with all these constraints and with this requirement and completely unknown obstacles, guarantee that we're going to be avoiding these obstacles if it's at all possible, with probability 1 minus epsilon. Okay, so the answer is yes, it's surprising you can actually come up with a theory to do that. There's a few caveats, but they're pretty mild. So one is we have to have a finite velocity of our obstacle. If you shoot a bullet, we're not going to avoid it. Okay, so, and the second thing is we have to have sufficient observation time. We can't give you a hard number because it depends on the complexity of the dynamics of the system. The more complex, the more observation we need to get a guarantee that we can sort of avoid it. And at the moment, this is where we're struggling, and future work that we're working on now is that actually the other agent has some fixed behavior.
What does that mean, fixed behavior?
It's not adversarial where it'll like change its strategy in midstream, because we can't predict that right now with what we have. So we're thinking about that. We're thinking about how can you use other principles to constrain what sort of various things that the drone can do or the other agent can do. The technique we'll describe actually can handle a lot of this. We just can't get a proof that we can avoid it. Okay, all right. Now, sorry, the next 15 or 20 slides are wonky, and then the videos come. So let's just sort of bear with this a little bit, and I'll hope to try to make connections with what I've seen, learned from some of you while I've been here. And so let's assume then that actually, if I knew the state of this thing that I'm worried about, that I want to avoid, and let's assume that actually its future motion can be described by some function f. I don't know what the function is. And so that actually at some sort of clock tick later, like a 50th of a second later, if I knew this function f and I knew its current state, I'd be able to kind of predict where it is. So if I know where it is now, and I want to actually predict where it's going to be n steps later. So you'll see throughout this talk, this notation here means hat means estimate, state is x, k is this is the time I'm at right now. I'd like to predict where it's going to be n steps later. So what you would do is you would just sort of compose this f if you knew it many, many, many times, and then come up with sort of a prediction of where this thing's going to be. And then, as I'll show you a little bit later, then you can use that in your sort of planning operation. So many of you have seen the common filter before. If you're familiar with the common filter, this is what the common filter does in one step of the common filter called the dynamic propagation step. So you have the dynamics instead of a general nonlinear A, it's just some linear matrix that propagates the state forward. And then if you have a control input there, then if you know the control input, then this gives you sort of your estimate one time later. And then you just sort of iterate this many, many times to come up with a future prediction of where it's going to go. All right, so now the thing is, how do we learn that operator quickly? So that's the whole game here. And how do we do it quickly, and how do we do it precisely, and we sort of put bounds on what we can do with it. So for those of you, I know people come from all different kinds of backgrounds here. So this is a quick slide on sort of learning about dynamical systems. And so in general, almost any sort of mechanical system that we can think about can be described with governing dynamics, that there's some nonlinear function of the current state and possible control will tell you its current velocity, and then you just integrate this forward to sort of get the position over time. So if you don't know this function very well and you want to sort of learn it, one approach is if you know something about this function to begin with, what you try to learn is what we call the residual. So if you have this situation and you can go to residual learning, that's what you want to do. It just works much better. We sort of set ourselves a task of like, we don't have any prior knowledge because we've never seen this obstacle before. So we have to kind of learn this whole function kind of on our own. And so I think these issues are pretty obvious. And so we want to sort of think about as control engineers, how many samples do we need? How fast can we do it? Can we be safe while we're learning, et cetera? I'll mention a few of these a little bit later. Okay, so I'm going to propose a particular approach. There's many, many different approaches. So the one I'm going to use something called a Kuban operator. I'm going to give you a short tutorial on Kuban. I was surprised actually with Nicole's talk this morning. Philosophically, this is basically what VSAs are doing, which is you're taking a complicated thing and you're lifting it to a high dimensional space. So now what I'm going to do is I'm going to take nonlinear dynamics, I'm going to lift it to a space where it's linear. And it's just a much higher dimensional space. And so we'll talk about it, but Bernard Koopman figured this out in the 1930s, and then it was an esoteric subject until the 2000s, and all of a sudden it got revived, and now last year 4,000 papers were published on this subject. So it's a very active area. And the reason we want to do this, of course, is that we all know linear control theory. It works really well. Instead of having to develop predictions for nonlinear systems, what if we could have a linear system, not linearize a nonlinear system, but actually have a much higher dimensional linear system where our tools are really sort of good.
Koopman was the 1930s person?
Yeah, 1913, Bernard Koopman, he was a mathematician. He actually worked with von Neumann, so he actually published with von Neumann. And so they sort of figured this out, and I'm going to give you a quick tutorial on the next slide. And one of the things is, again, really like this is because a lot of learning doesn't necessarily handle the fact that the system you're trying to learn actually has limitations and constraints on it, and we can learn constraints more easily in this framework. A lot of deep neural networks, the field is advancing nicely now where you can do much more better online learning. This is all online, so it's very much an online sort of learning system. There's many things they can't do, so I'm not going to propose this is the universal best way to do prediction, but for the things we're interested in, this works sort of very well. And we'll see a little bit later is we can also adapt to mild non-stationarity. So that's actually how we handle adversarial sort of opponents that actually, even if they change their minds, start doing different things, we can kind of handle them, but we just can't prove anything about it. Okay, so here's what Koopman figured out. What am I doing? Okay. So let's assume now, forget about control. I'm going to come back to that in a second. So let's assume like this was a football or a frisbee. So there's no control input. It's just a dynamical system, but we don't know it. And so if we did know the dynamical system, if you remember your ODE theory, what we say is, well, the solution to that ODE, we may not be able to kind of write it in closed form, but formally it's a flow, which means there's some abstract function. If you give me the current state, say at time t0, and I want to know where it's going to be a t, I can apply this operator on here. And so we think of these ODEs as really being basically the derivative of the flow map is equal to the operator f acting on the flow map here. And so
this flow map, this S of t is, okay, you're going to show us it.
Yeah. So what you're all familiar with this was sort of the phase space of a dynamical system. And so starting since Poincaré in the 1860s, most of sort of, dynamical system theory is based on looking at the state space. And it's great. There's nothing wrong with it, except for when the system's highly nonlinear, it can just make life very, very tough. Now, Koopman was not working in the data-driven era, but he actually sort of found something back in the 1930s, which actually is perfect for the data-driven era. So what he sort of says is, well, instead of thinking of the state space, because a lot of times in practice, we actually can't directly measure the state of something, but we can actually define something we'll call an observable. An observable seems mysterious, but it's straightforward. So this could be energy, right? So I may not be able to measure exactly the state of my drone, but if I knew its mass and I knew how fast it's flying, I could actually compute its energy. And so I could sort of say, well, abstractly, I'll define a function on the state space of energy. It could be momentum. It could be anything at all. And so the idea is that actually now we're going to define a function space of all possible things that you can observe about this thing. And those things that you can observe are a function of state, but we don't necessarily need direct access to the state. And so the idea then is, at first it seems mysterious when you think about it for a second, it's just simple math. That actually now, in this space of observables, there exists an operator. This is a function space. So think of functions as like an infinite dimensional vector. So there's basically an infinite dimensional square matrix that multiplied by this vector is the same as taking the observable and composing it with the flow. So the idea would be is if I know the kinetic energy here, and if I want to know where it is a time later, I take the flow map from here, I propagate the system t seconds later, then I just say, what's my observable, what's the kinetic energy function? What Koopman showed is that actually I can take the kinetic energy at time t0, and this operator will actually propagate the kinetic energy, not the state sort of directly. All right, and so now another thing that'll play a minor role, don't want to get into too much Koopmanology today, but here's the key point. So now, because this is a linear system, you all know any linear matrix has eigenvectors and eigenvalues. There are eigenfunctions, as they're called, of this operator, and they have sort of nice properties, and we're going to sort of use them later. The key thing then is either using these observables or using eigenfunctions or other methodology. What you can do, like in the VSAs that you learned earlier today, is you can take this dynamics and lift it to this higher dimensional space. So I can't plot in 15 dimensions here, but then in this higher dimensional space, there's a linear dynamical system that we all know and love. Now, the price that you pay is that it's, in theory, it's always infinite dimensional. Now, in practice as engineers, we actually truncate it to sort of finite dimensions. And so the game is how to find those truncations. Okay, one more bit of pedagogy here for a second. In robotics, we always work in sort of discrete time rather than continuous time. And so it turns out the Koopman theory is even easier in discrete time. So if I have, I'm sorry, mixing notation, I use the function f before, but if I have something that actually just propagates the physics of my variable at each time step, then if I have, again, an observable on this, then the Koopman operator sort of advances is, or will just like in the continuous case, for that discrete time, the eigenvalue relationships are even easier. And here's the key point I want to make. Because this is a function space, if I have anything that I want to propagate, so it could be the state itself, it could be energy, it could be any other function that I want to sort of propagate in my dynamic models because I want to make prediction. I can always expand that function as some sum. It might be an infinite sum of all the eigenvalues. In either case, eigenfunctions. So this is just a linear sum, but again, it might be infinite dimensional. And the key thing to think about then is that if I want to propagate, predict in the future where this function is going to be, j time steps later, I just apply this Koopman operator j times. And then what you see miraculously in the end is if you know the eigenvector or eigenfunction, you just multiply its eigenvalue j times, its scalar, multiplication j times, and you get this prediction. So prediction is trivially easy in this sort of high dimensional space. Now, there are two ways to actually do prediction and work with these things. One is to work with these eigenfunctions. If you don't get this eigenfunction just right, and there's numerical issues there, then your prediction sucks. And so the other one is to actually work with approximating this operator. And so that's the path that we're going to take today. Okay, I'm going to gloss through this real quick. And so what happens when we add control? The control breaks this nice linearity. But actually, about 10 years ago, we found out that under a broad range of assumptions, which are good enough for us, that the lifted system actually is what's called bilinear. So it's sort of nearly linear. Now, and the problem we're dealing with is we're trying to predict what some other agent is doing. We don't have access to what control inputs they have. And so we're going to assume that actually that system has some controller on it. I don't know what it is. And so if you think about that, we're just back to the case that we're trying to predict this function. So I'm going to just stick with this without control because that's good enough. Again, that's where the fixed behavior comes from because we're not switching functions back and forth. Okay, so here's the tool. I didn't invent this tool. This is a standard tool. It's about 15 years old, and I'll come to dynamic mode decomposition. This was first invented by a fluid mechanician who didn't even know what a Koopman operator was. And then later, after he introduced this, the Koopman people said, aha, that's the method for us to do this. This isn't necessarily the best method, but it's a standard method. And so the idea goes like this. So let's say you now have some system. So the system could be as like, hey, someone threw a Frisbee at me, and I can start to get data from that system. And so if I have a sort of, I'm measuring data at discrete times. And so I have the state of the system that I could measure at time k. And then at some time later, it doesn't have to be a constant delta t, it can be time varying different amounts of time. I have another data. So these are like the data pairs you do learning on, right? So this is just a data pair in time. So if I take a whole time series of this and sort of arrange all the states in the before a motion, and then arrange all the data in the after the motion, then what Schmid hypothesized is, well, what we'd like to do is to find the best linear operator that actually sort of transforms the data from the before to the after. This may be a nonlinear system, and so this won't get it properly, and we'll come back to that later, but it's the best approximation. And so it's a simple thing. So basically you sort of say, well, to find the A here, which actually transitions the before to the after data, I just do a least squares. We do a fancy Frobenius norm here, which is sort of, here's the data after, and this would be the propagation of the data before to match the data after. So I'll just try to minimize that. And that has a closed form formula. So it's
data after what?
So like a step.
Okay.
Okay, so if I'm tracking a walking robot, it's a step. If I'm a drone, it's like I have a video frame 30 times a second. The before is this frame, the after is the next frame. And then you can think of this frame as the first frame and the after that frame is this next frame. It's just a sequence of data. Okay, now there's two more technical details I have to get through. People thought that was great, but the problem is a lot of times we don't have access directly to the states. We only have access to these observables. And so extended dynamic mode decomposition basically says, like, look, if you have these observables, which are the things we can oftentimes get, you can do the same thing. You compare all the data in one time step with all the data at the next time step, and then sort of find, using the same idea, sort of a linear function. Okay. Now, here's the difficulty for our problem, and this actually addresses something that Toby's been talking about sort of this week. What if we actually can't measure all the state? So DMT and EDMD assume that actually either all the state is available to you, or you're measuring this observable, but the observable has a function of all of the state, so that there's no hidden state anywhere. If you could only get measurements that actually aren't connected to some of the state, then like how do you actually predict when there's some of the state you don't have a direct link to? Maybe you may have seen this thing before. So back in the 80s, a guy named Hawkins won a Nobel Prize for this and came up with Hawkins embedding theorem. He was studying chaos at the time. And so the idea is that actually now, if you have some true underlying dynamical system, this is the full state, but I actually can't get measurements of all these states. I can only get some substates or even functions of the substates. So now imagine, like I said, I can measure something about this thing, and I can sort of measure a time sequence of these things. Hawkins sort of said is like, well, if you can measure long enough, then you can actually construct a dynamical system model that's not the true model, but it's diffeomorphic, which is a fancy word saying it's deformable into the true model, as long as you measure 2D plus 1, where D is a dimension of your dynamical system. All right.
By the way, were people here when Gerald Powell came as part of Terry Sinopsis group? Anybody remember Gerald Powell, the guy from Okinawa? You remember, Jason, he did this lovely talk exactly about this Takens embedding theorem. He showed all kind of practical applications of it. You may remember from like 2 years ago. He came to visit us recently in Zurich and exactly talked about this Takens or Takens?
Hawkins.
Takens theorem. Yeah.
Okay. And
Exactly
so
this,
now
yes.
again, you don't know ahead of time the dimensions, so you don't know how long you have to measure, but people have developed, and we'll give you our own version of it, how you can check when you've sort of done enough measurement so that you can actually get a model of the dynamic.
But the trick is you have to go to what? You have to go to two.
You got to make sure you measure long enough, because if you don't measure long enough, then there's something inside the state that you can't see.
The privileged state gets exposed somehow.
It eventually
Guaranteed
gets
to be
exposed.
exposed.
Yeah.
What is D? Sorry.
What
D
is
is a dimension of the dynamical system. So for like a Frisbee, that's a 12-dimensional system. And so you'd have to measure at least 25 times to capture picture. Usually you want to measure more. And then what we're going to talk about in a second is you have noise. And so noise makes your problem. And that's actually our contribution we'll get to in a second. Okay, and so
What's the typical intuition for what does it mean that true control systems are diffeomorphic?
I didn't quite follow you.
What is diffeomorphic meaning again? Yeah.
It means it's deformable. So the thing is, it's like,
How can we imagine it? How, like in the real world, which two systems are?
so what it does is it basically says the dynamic model that you compute will, if you look at its phase space, it will evolve in a way that's the same as the true underlying system that you don't know, but maybe just squished around a little bit. So it's close to the real system, but it may not be exact. But it has, for most of the properties you care about, it actually has the same properties. And that's the thing we're going to use, is that actually for the properties that we care about, it's as good as the original system that we can't measure directly. Okay, so what we do then is we sort of take whatever state we can measure, and then we sort of form what's called a Hankel matrix. So we take the first measurement, so you get a time series, and you go up to sort of Q measurements, and then I'm going to show you what schematically what a Hankel matrix is. You sort of start the next row, you drop the first one, and then you drop repeat this entire column except for the first one, and then add a new one, and then you drop it, and then keep repeating, and so you sort of layer this Hankel matrix. So what you can show is, if you think about it, is two things. One is the off diagonals, the counter diagonals are the same data here. That's going to play a role a little bit later. And if you think about it, because our Koopman operator propagates our observables from time to time to time, you can think of the Hankert's matrix actually as having the Koopman operator embedded into it in a bazillion ways. And so the idea then is that if you grow this matrix big enough with enough data, this matrix will converge and have a submatrix in it, which actually captures your true dynamical system. And so the way that people find this, again, this is not our invention, is that actually then you just do a singular value decomposition. And then you look here in the sigma matrix, which has all the singular values. And then you see when the singular values go to 0. So the dimension of the number of positive singular values is the dimension of your system. All right. So this is one way. So again, for brain scientists, you can actually use this on brain data because, again, the brain, you're only measuring a small amount and there's billions of hidden states below there. So this can kind of actually give you, a way to sort of capture the dynamics of what's being used in the brain. There's some technical difficulties we can talk about later. Okay, but here's the problem. Okay, so we have noise. We have this really noisy system. And so what we like to be able to do then is to sort of say, okay, we can, and I didn't sort of mention this. So once we find sort of the rank of this matrix, we can then find the submatrix that actually captures the dynamics of the system, use this dynamic mode decomposition, and come up with a linear operator that we can use to predict the system. It's a little more subtle than that, but that's just the basic idea. Yeah, sure.
So in the matrix that you showed there, it looks like it specifically depends on this XOT1. Is it very sensitive to like initial state where you start measuring, or is
No, it's a great question because the idea is that we start with that matrix we're going to see later, and then it becomes a sliding window. So then we go a second, we throw the first data out, and then we go in another second, we throw the second data out, and we keep forming Hankel matrices. So we're not going to just do it once, we're going to do it time over and over again. So then you can actually look and see if you get a consistent answer over time.
But in the end, you end up doing a lot of, linear algebra calculations.
Yeah, which is fast.
Yeah.
Yeah, and that's the beauty of it. And that's why we work with Koopman, because Koopman's geared for linear algebra. Okay. So, but we have noise in our system. And so what happens is some of those singular values are noisy, so we don't really know the true dimension. And so our prediction is not going to be good. And so the key thing that we want to do for safety critical control is to be able to say any schmuck can make a prediction, but we want to quantify how good the prediction is. So, we will have noise in our sensors. The agent itself may actually have perturbations. In the early stages, we actually don't have very good learning as we're still learning about the system. And so when we predict forward, there's going to be some uncertainty here. And the problem with the safety critical control is that actually now if you get an over approximation, so it's very conservative, but then when your robot plans operations, it's very conservative. And so it's kind of like it's just too timid and doesn't do much. And if it's you're too aggressive and you under approximate the uncertainty, then actually you'll collide a lot because you're just too optimistic with how sort of far away things are and how aggressive that sort of you can be. And so the real first contribution of this work was to sort of figure out how can we actually denoise the Hankel matrix and actually use that denoising process to give us a new uncertainty quantification method. And so the idea in the Hankel matrix, as I showed you before, is that its structure is such that there's repetitions of the different elements here. So there's actually coupling between all the noises in the data in a Hankel matrix. So it's very difficult to denoise the Hankel matrix using what's called random matrix denoising theory that I'll briefly mention on this slide. We dug a Schuyler way, the graduate student, I didn't find it, found out back in the 80s, people had this thing called the page matrix, which is lost to time. And it's called a page matrix because you just take a data series, like I'm just measuring my drone that's coming at me, and I take a bunch of data. Instead of this complicated Hankel matrix, you just loop the data up and down. Okay. And so if you do that, there's no repetition of any data in the matrix. And therefore, what you can think of this matrix has the true signal in there with no noise, because I have these crappy accelerometers are adding noise. And then if I assume that the noise is IID from step to step to step, then you have a sort of a second additional matrix that, again, if the covariance of noise is constant over a sampling period, that you can think of this as sort of a sum of two things. I won't go through the theory, but Donahoe, a well-known statistician at Stanford, and his student Gavish about a decade ago came up with a beautiful way to denoise noisy matrices. And so the idea is that basically you go in, you perform the singular value decomposition, you do some statistics on all the matrix elements, and then you can come up with a number, it's just a threshold. And then you just sort of threshold the data, and what comes out then is sort of the dimension of the page matrix. Our contribution is that actually if your system's observable, the rank of the page matrix and the rank of the Hankel matrix are the same. So that we can do this easy calculation here, and then take the results, and then actually use that dimension to go back and construct the right dimension Hankel matrix from which we can get the right dimension linear approximation or Coupon operator for the data.
But how to possibly come to this result? I mean, you had to learn all this stuff that was done decades ago, right? People are really experts in linear algebra here and all this kind of work. This stuff is well known in this area. You know, to us, it's all Greek, right?
Yeah, the Hankel people, this is just in control theory, people, Hankel matrices like that's you learn in the first year of tech school.
Okay.
This stuff, like I said, this is a rare find. Okay, so like I said, we can then use this to sort of now construct a denoised version of this data.
Yeah, but somebody who's a mathematician did this proof, but they must have had some intuition to realize that this is possible.
Actually, it was an engineering grad student who did the proof, All right, so so enough boring crap. All right, so let's get back to making this work in the real world. So let's go back to our, let's avoid, somebody being thrown at us or another drone flying towards us or something like that. And so, here's kind of the pipeline now. So if someone's throwing a Frisbee at us, the problem with the Frisbee, as I said, is its spin state is very hard to decipher. But if you look at the dynamics of the Frisbee, the spin state really affects how it moves. So we'd like to learn the dynamics, even though we don't have access to them. All we have are sort of measurements at some point on the Frisbee that we can repeatedly find and a bunch of noise. So we construct this Hankel matrix. So we have to view it for a certain amount of time. We don't know exactly what the dimension of the dynamics is. So we go a little too long. All right, so there's the danger. We may wait too long. Then we do this singular value decomposition. Then we sort of find the we construct the Hankel matrix.
Hankelization, okay.
All right, because I'm going to introduce a new term to you in a second. So then what we do is do this thresholding, and what it does is it separates sort of into the real underlying signal, that's the true dynamics, and then the rest is sort of noise. Now, most people would throw the noise away. What I want to tell you is this is the gold mine. And that actually, what we can do is with this technique is we can actually sample the noise every instant. So this we do as a sliding window. So we construct every 50th of a second this whole pipeline. And so we're just sliding the data about 50 times long. So we take about 50 steps to sort of learn enough so we can induce prediction. And then we keep updating the predictions and we keep updating noise samples. So what do we do with the noise samples? So this is a term we introduced called dehankelization. It's a bastard name. And so the idea is that you have the Hankel matrix, which we construct, we can turn it back into a time series. So then we can then turn it into two time series. One branch of the time series has been denoised for us, as well as we trust the theory, right? It's never perfectly denoised. And the other branch is turned into a noise sample. So from the clean noise, we construct our Coupon operator. And then from the noisy part, what we do is we do a bootstrap. And so the idea then is the Hankel, the Coupon operator tells us sort of where we predict this to go cleanly, but there's noise in the system. We don't know if the noise is from wind disturbances or whether it's from our bad sensors or our inaccurate learning state in the early stages. And so what we do is we take all the noise samples and we sort of construct an empirical distribution of what's happening. And so here's the hard part. So we want to figure out, well, how do we avoid this thing? Well, which of these paths do we avoid? All right. So conventional sort of stochastic NPC would say, avoid the mean, because that's your best prediction. What we found is that's a bad idea. And that's the second message I want to get across to you tonight, and actually dovetails with Michael's comment today, is that actually I'm going to give him some empirical evidence why risk-aware planning is the right thing to do. All right, so what we do, and now this gets into the wizardry of MPC. I know this is not an MPC audience. I'll just mention one thing. So now we have all these different possible things that we don't know which of these is the true one. And so we want to think of them as a probability distribution of possible outcomes in sort of the future. And so in the NPC world, there's a thing called a chance constraint. And so the idea is, if I have some function here, this function is like the distance to the obstacle that might hurt me. What I'd like to do is to make sure that actually, if that function being greater than 0 means collision, that actually the probability of that function is less than some epsilon that actually I get to choose as an engineer. So I want to choose this like 0.05. So say I'll accept 5% probability of sort of collision here. And you don't know what the distribution is, but in the classical theory, you assume you know what the distribution is. And we're sort of lucky because we get these noise samples in real time. So we can actually empirically construct an approximation of this distribution. And so we can then put a probabilistic chance constraint on our MPC. And so again, you can kind of choose how much of the tail do you want to screw yourself, how much are you willing to accept. And so now here's the wizardry, don't worry about the equations. So NPC basically says, I want to figure out the robot motions to optimize some function, satisfy the dynamics, satisfy constraints, and make sure I avoid things. Well, my avoidance is a probabilistic constraint. And then we have to do a bunch of engineering that actually turns this into deterministic equations we can deal with. And then this is the key constraint. So what we do is we say, well, we know the samples that we've got are really noisy. So we apply what's called distributionally robust optimization. So we say, let's avoid these things with respect to all probability distributions that actually have the same mean and covariance as the empirical mean. So we know we only have a finite sample, so we don't know that really that it's that truly sort of Gaussian approximation. So we'll say every distribution that could have that same mean and covariance. Okay, so here's how it works in practice. This is simulation. I'm going to show you the real world in a minute. What we've done here is this means more and more risk averse. So here we're just dropping something and we're adding noise as the thing drops.
It's in the middle. That's your drone, right?
That's our drone, and its task is just to sort of station keep. And so what now we're doing is, like I said, just dropping something. And so if it's very risk averse, you sort of see it goes very far away. And then if it's not so risk averse, it just sort of barely sort of sidesteps sort of what's happening. Here's take home number 2. So in these simulations, we did thousands of Monte Carlo simulations by throwing all kinds of different things at this. And what we found is that actually, by taking a risk-aware approach, if you take sort of a classical expected value approach, you get hit a lot because you're always worrying about the mean, but it's the tails that hit you. And so if you worry about the tails, what happens is you actually have very low chances empirically of actually getting hit. So this is reason 1 for risk-aware motion planning. Reason 2 will come up in a second. Okay, I'm going to skip this because it's where we've had enough beer tonight. So the next step was we want to, again, as a safety critical engineer, what we wanted to do was to sort of say, okay, let's get rid of the constraint that we have near Gaussian noise. And so in order to do that, we have to come up with a different uncertainty quantification technique. It's something that we worked on called adaptive conformal prediction. It's too much to go into tonight. We need a more general notion of risk. I'm going to talk about this. And we need a lot of NPC wizardry. This is not the right audience. You're not NPC people. Okay, so but the whole thing then to this next step is to notice that from the finance community, they actually thought a long time about risk in the financial markets. And so the control community started adopting the finance community notions of risk starting 15 years ago, and it's still a fairly active area of activity. And so in general, a risk measure, so if you were used to the idea of expectation, an expectation is risk measure. Sort of telling you that actually the risk of what could happen is what's happened with the mean, the distribution. A risk measure is another way to sort of put a cost on that distribution. So you can better hone in which part of the distribution really screws you and which part you're okay with absorbing the sort of fluctuations. And so in particular, if you go look at the risk, you want to actually focus on something called a coherent risk measure. There's a set of risk measures that have certain nice properties to them. And I'm going to give you a takeaway in a second why you want these sort of coherent risk measures. But here's the real issue in sort of modern sort of safety engineering. So before we do that, just a measure. So what do these risk measures look like? Value at risk is actually what most of our financial community is built upon. So every day the banks actually have to go to the regulators and sort of say, look, if our financial instruments over the next week or two have the same distribution of outcomes that they had the last week, then if you tell us a certain number, like I have a 5% value at risk, you basically measure what's the area, 5% area under the tail. That's the value at risk. This is not a coherent risk measure and it has some problems for control. The one that everyone uses, I know Michael uses this one of his projects, is a coherent value at risk. And so the idea is that actually it's sort of the average value in the tail below some value at risk here. So it makes it on average how badly you're going to get screwed by the left tail. Why is that important? Because then traditionally, up until recently, in sort of NPC and stochastic control, the idea is, look, we have some cost function we want our robot to sort of satisfy, and then we have constraints, like we don't want to get hit. But these are sort of random now, because we have random noise that's happening inside there. And so in minimizing this with this constraint, the two classical paradigms until recently have been, let's assume the random noise is sort of a Gaussian, and then we'll just, if that's Gaussian, then the right thing to do is to take the expected value. Or a lot of control theory. So John Doyle, who's been at this meeting, he got famous in the 80s for developing this sort of version of robust control theory, which sort of says, whatever your distribution is, I want to make sure I can handle everything, that I can handle the worst case. And so that's okay, but this sort of too extreme. There's, as Michael mentioned the other day, there's a big range in the middle. And so, again, traditionally we've had these two ranges here. One is worrying about the mean of the sort of outcome. The other one is the worst case. What risk allows us to do is to figure out how to dial sort of in between them. And here's the reason why we want to do this. So again, I introduced this idea of a chance constraint. And so we can sort of say, I'm sorry, I got cut off here. That actually now what we wanted is, so the probability of some event is less than whatever amount of tail risk that we want. Now, here's the difficulty with this theorem and actually why in the real world, these theories are no good. In the real world, you don't know your probability distribution. We actually have some samples of it, but it's a small sample. So we know the real noise is not exactly the noise that we sample. And so what you'd like to be able to do is to sort of say, let's actually guarantee that we're safe, even if we have a whole different range of possible probabilities here. So this is what's called distributionally robust optimization. So you can define things like the expected value or mean over all possible things. And then you can actually, and what we did in that previous demo that you saw was actually come up with constraints. So they say no matter what distribution in a range of distributions are happening here, we'll guarantee that will be robust with respect to those outcomes, given some probability threshold that we accept as tolerable. And so this is a little wonky, but there's a very simple high-level description. So in the finance community, they developed this thing called the representation theorem, which sort of says then that every time you use a risk measure, what you're really doing underneath is you're actually doing an distributionally robust optimization. So in some sense, when you switch to a risk approach, you're also basically saying, look, I don't even have to really know what's happening with my uncertainty. I can actually have a big spread there and I'll still get good outcomes. So it's a much more clever way of thinking about the world, assuming that you just don't know that much. Okay, and what the representation theorem says is that you can actually then find sort of these sets of distributions that you're optimizing over. Okay, let's get back to fun. Now, my background is in field robotics. So one of the things you may not know is over the years, DARPA, which is our military, has had 5 grand challenges, they call it. I'm the only person on Earth that's been in all 5 challenges. And so this is the last one, which ended in 2021-22, called the Subterranean Challenge. And so in this challenge, what they figured is, again, these things have a military application and a nice application. The military application is that actually in the future, they expect to have to go after bad people that are hiding underground. And so the good one is if you remember the teams in Thailand about a decade ago that got trapped in an underground cave, wouldn't it be great if we have robot technology to go help them get out of that cave? So they had a series of competitions that you'll see in video in a minute, where they produce underground spaces, underground tunnels, underground sewers, natural caves, underground bunkers. What you could do is you could have as big a robot team as you want. Then there's a 1 meter by 1 meter hole you'll see in the video that your robots can go through. Once they go inside, there's no power, no light, no communication. If you want that, you've got to bring your own. Then one person on the outside can communicate to your team, but no more than one person. If the robots want to talk to each other, they actually got to construct their own communication network. You have 1 hour to survey this whole area and find 40 objects that you've never seen before, but you know the class of the object. So we knew there's going to be a red backpack. We knew there was going to be a cell phone. We just didn't know what they looked like. We had to go find them. And then in that 1 hour, once you find them, you actually have to tell DARPA that you found it, what it is, and its location to within 5 meters over an 8-kilometer distance. So very accurately. So you had to build your own maps as you go down there. So one of the things that we did is started first using risk is when we're dealing with caves, et cetera. And we use both wheeled and sort of legged robots. What you'd like to be able to do is, as you're planning the motions of these robots, is to assess how much risk is the robot taking in making its forward motion. And so we introduced something called STEP. And so the idea is we would have multiple sensors on there. We have multiple cameras, multiple LiDARs, infrared cameras, all kinds of sensors on these robots. And so we would look at all the different characteristics of the terrain. And as you're going, these look like sort of continuous data. These are actually little pixelated maps. In every pixel, we actually gather statistics of actually the slope and the terrain and the roughness. And then we do actually calculate the coherent value at risk, actually, and then sort of use the risk adjusted value to sort of figure out where is it sort of safe to go. And what's nice about this approach versus a conditional or a conventional sort of averaging approach is this risk value we would dial up as the competition went further. So as we got towards the end of the 1 hour, we just let the robots go crazy. We just said, take as much risk as you want. And so here's, for example, just to show you how this works. This is a lava tube in Northern California. This is a spot robot. They're dumb as a brick, but we added a bunch of intelligence to them. And so what you see color coded here is sort of the risk. And so this is trying to explore the cave. And so it's using then the risk values to sort of figure out.
Risk is like basically how steep it is or something? What is
It's
it?
all kinds of risks. So it can either be steepness or roughness if we judge it to be smooth. We want to avoid water. You'll see that in a second. So water would be a risk. So there are all kinds of different risks. So we just lumped it into one risk. So we can then sort of use sort of risk. And so I said, so then the idea is you see all the little arcs there. This is an NPC planner. It's trying out many different sort of possible paths, judging the risk on each one of them.
What is that scaffold, that ladder?
That's just the prediction of exactly where it's going to be 50 times in a row. So it's actually like 50 times a second. It's trying to say that's where I predict the robot's going to be. Okay, so here's one of the competitions. This was the most fun one. It was actually an abandoned nuclear reactor up in Washington State. The company who was building this reactor went bankrupt right before they put the fuel rods in. And so they loaned out this 3-story reactor core to movies and stuff. So there was tons of junk down there. So DARPA rented this thing. And so as you'll see in a second, we had to go and send our robots in there, and we didn't know how many floors there were ahead of time or how big it was. And we had 1 hour to sort of scavenge this entire area and sort of look for these things and then report on them. So here's sort of a video of it. You don't have to listen to the cheesy music we put on this. Okay, so what you'll see next is we have 5 robots in the course. You're going to follow one of the robots. Now, we couldn't see most of this. This is video DARPA gave us later. So this is the entrance everyone has to go in. This is ground zero. So we have to report everything with respect to these coordinates. And unfortunately, the video is sort of jumping. And so this robot understood stairs. And so it said, hey, I found a stair. Then it got okay from the team to go ahead and explore that stair. Again, the robot doesn't see this view. We got this from DARPA later. You'll see what the robot sees in a second. So as it's going down here, now what you'll see is this is what the remote operator can see, but it can only see one robot's view at a time because of the network bandwidth. And then it's building a map of these stairs as it sort of goes down. When it gets to the bottom of the stairs, again, it doesn't know how far down the stairs is. It sort of senses there's no communication down here. So all of our robots have communication droppers. So now it's going to squat down and actually drop a mil-spec radio with internet over it. And so then it's going to
relay. It drops a relay.
It drops an internet relay. So now it's going to go off and explore this floor while other robots are exploring the other floors. And so now what you'll see next is the parts that I contribute. This is a big team. And so it knows about buildings and caves and things. And so it also knows that DARPA told us any water you see might be up to 6 feet deep. So as it's exploring around looking for the 40 objects, it says, aha, there's water. That's really risky. So I better avoid that.
Does it know that it's water?
We had special sensors that helped us detect water. And so now it's just going through and sort of, exploring. and sort of building a map. You'll see the map in a second. And so here it's sort of explored a good fraction of it. And now another robot left a radio, and it definitely gave the message saying, look, I'm a wheeled robot. I can't go down these stairs. Can you go down these stairs for me? So it's going off. And so the team builds a multi-resolution map. So one resolution is just this very sparse one. These are all the places we've been to. As it's going, it gathers more information about what it's seen before, what it's not seen before. So these little things here, these are areas I've never seen. So it's also dropping this information in case other robots come by and explore a part that actually this robot didn't explore. And then you'll see in a second actually how all this are put together into kind of a global map. And so here the robot will go off and explore just a little bit more. These are sort of a few more of the rooms that it explored right near the end of its exploration. Then it also has a map at this resolution. So it has a detailed point map of every room that it's sort of been in. And so this is the area that one robot explored. And then now what you'll see is all 4 or 5 robots together actually merge their maps. And then also annotate on top of the maps, actually what are the things that they sort of found while they're doing the explore. Okay, what does this have to do with obstacle avoidance? Nothing. It's a fun video, and we use that notion of risk all throughout this thing to sort of plan the robot footsteps and positions, and also to titrate the risk as a strategy.
But you were using this Koopman stuff there, not in this, right?
Not in this. Now I'm going to get to that next.
Okay.
Okay. Okay. So this is another fun one from the finals. Some risks can't be quantified.
What's that?
It's a plastic bag. The drone completely blows up. So there's no way you can mathematically model that one. All right, so I'm going to skip ahead. And so this is sort of the fancier version of the theory I described now that it makes no assumptions about the world. And so let me just play this video here. So what's happening is this robot has these algorithms on board. There's motion tracking cameras here. In this earlier stage, we hadn't gotten around the perception yet. So this grad student here has a stick. At the end of the stick, there's some markers. And so the robot thinks there's a 1 meter sphere at the end of that stick. And so what you'll see over here, it's not perfectly synchronized. This is the task that the robot's given. This yellow is sort of where the robot judges the human to be. And this is the obstacle here. And this ball, you'll see, grows and shrinks. This is the radius of that obstacle. So the risk posture in real time. So during this particular experiment, we asked the student to be adversarial. So the student's trying to get in the way of the robot, forcing the robot off of its task. And so what you see is it sort of backs up and then tries to get back onto its task after the threat has sort of gone away. Here, we've asked the grad student to be sort of friendly, and so not get in the way, but at least slow them down. So that what you see, it's sort of backing up because it's like it wants to go. It's like, no, the human's there. We got to go back, wait for the human to go, sort of go back. Now, this theory can handle multiple obstacles and actually n obstacles. It just depends how much computing power you have. So here's 2 grad students torturing the poor robot. And so they're switching between adversarial and friendly operations. And so you see the robot is having to do all kinds of gyrations to figure out how to get away from these 2 kind of in real time so that it tries to stay on its task and actually avoids these obstacles.
And the only thing that's changing between these demonstrations is behavior.
This favors. And so this works in 3D. So here's a drone, and again, it thinks there's a 1/2 meter sphere out there. And so it's, I'm sorry, the laggy video here. And it actually gets mad at Billy and forces him out of the way. But so I said, it works in real time on a very modest computer, kind of in 3D as well. Okay, let me finish up. We're out of time. And so, and again, this is a video just from a few weeks ago. So this is really using the same ideas that we had here before, but now actually we have real-time computer vision systems tracking this thing. And here we're not trying to avoid something. Here we're actually trying to bring 2 things together to kind of collaborate. In this case, it's being able to, while this sort of sea is rocking around, get this Tomahawk, forward Tomahawk missile safely and gently into kind of its silo down there.
And the point of going through all this mathematical, quite sophisticated mathematical approach is that you can now guarantee.
I can guarantee up to the assumptions in the proofs that this will be safe.
The missile's not going to hit some obstacle.
Yeah.
Okay.
because a Tomahawk missile mistake is $100 million mistake. Okay, and so it's on my screen. There we go. Okay. We've chosen this equipment operator because we can learn really quickly. So we can basically learn in 20, 30 samples, most dynamical, simple dynamical systems. It works well on small computers, and it has a nice theory that goes with it. So I can get these proofs that, again, our sponsors and other people want to get those guarantees. So that's my message to you coming from the robotics community is, look, I think many of these things could be done neuromorphically, but the standard now is you need hard guarantees that actually, if you want them to reach the real world, that these things will work as advertised. The things that we haven't done yet is, like I said, is if you have a very adversarial target, the sort of continual monitoring of this approach will, in practice, avoid that person, but we don't have any guarantees of it. And we're just kind of exploring right now sort of more detailed theory about coordination, cooperation, rather than just sort of avoiding things. All right, thank you.
Thank you.